A life support system is the combination of equipment that allows survival in an environment or situation that would not support that life in its absence. It is generally applied to systems supporting human life in situations where the outside environment is hostile, such as in space or underwater, or medical situations where the health of the person is compromised to the extent that the risk of death would be high without the function of the equipment. In human spaceflight, a life support system is a group of devices that allow a human being to survive in space. U.S. government space agency NASA and private spaceflight companies use the term Environmental Control and Life Support System or THE acronym ECLSS when describing these systems. The life support system may supply air, water and food. It must also maintain the correct body temperature and acceptable pressure on the body and deal with the body's waste products. Shielding against harmful external influences such as radiation and micrometeorites may also be necessary. Components of the life support system are life-critical and are designed and constructed using safety engineering techniques. In underwater diving, the breathing apparatus is considered to be life support equipment, and a saturation diving system is considered a life support system. The personnel who are responsible for operating it are called life support technicians. The concept can also be extended to submarines, crewed submersibles and atmospheric diving suits, where the breathing gas requires treatment to remain respirable, and the occupants are isolated from the outside ambient pressure and temperature. Medical life support systems include heart-lung machines, medical ventilators and dialysis equipment. A crew member of typical size requires approximately 5 kilograms of food, and 3.54 kilograms of liquid wastes, and 1.00 kilograms of carbon dioxide produced. These levels can vary due to activity level of a specific mission assignment, but must obey the principle of mass balance. Actual water use during space missions is typically double the given value, mainly due to non-biological use. Additionally, the volume and variety of waste products varies with mission duration to include hair, fingernails, skin flaking, and other biological wastes in missions exceeding 1 week in length. Other environmental considerations such as radiation, gravity, noise, vibration, and lighting also factor into human physiological response in space, though not with the more immediate effect that the metabolic parameters have. Space life support systems maintain atmospheres composed, at a minimum, of oxygen, water vapor and carbon dioxide. The partial pressure of each component gas adds to the overall barometric pressure. However, the elimination of diluent gases substantially increases fire risks, especially in ground operations when for structural reasons the total cabin pressure must exceed the external atmospheric pressure. See Apollo 1. Furthermore, oxygen toxicity becomes a factor at high oxygen concentrations. For this reason, most modern crewed spacecraft use conventional air atmospheres and use pure oxygen only in pressure suits during extravehicular activity where acceptable suit flexibility mandates the lowest inflation pressure possible. Water is consumed by crew members for drinking, cleaning activities, even thermal control, and emergency uses. It must be stored, used, and reclaimed efficiently since no on-site sources currently exist for the environments reached in the course of human space exploration. Future lunar missions may utilize water sourced from polar ices. Mars missions may utilize water from the atmosphere or ice deposits. All space missions to date have used supplied food. Life support systems could include a plant cultivation system which allows food to be grown within buildings or vessels. This would also regenerate water and oxygen. However, no such system has flown in space as yet. Such a system could be designed so that it reuses most nutrients. This is done, for example, by composting toilets which reintegrate waste material back into the system, allowing the nutrients to be taken up by the food crops. The food coming from the crops is then consumed again by the system's users and the cycle continues. The logistics and area requirements involved, however, have been prohibitive in implementing such a system to date. American Mercury, Gemini and Apollo spacecraft contained 100% oxygen atmospheres, suitable for short-duration missions. To minimize weight and complexity, the Space Shuttle was the first American spacecraft to have an Earth-like atmospheric mixture, comprising 22% oxygen and 78% nitrogen. For the Space Shuttle, NASA includes in the ECLSS category systems that provide both life support for the crew and environmental control for payloads. The shuttle reference manual contains ECLSS sections on crew compartment cabin pressurization, cabin air revitalization, water coolant low